So let me start with a brief review of what I talked about last time, which is a recipe for solving a two-level Schrodinger problem given in the form of these two by two coupled differential equations. And this is some kind of a two by two Hermitian matrix. And I introduce you to a trick by which we can write this thing as some overall magnitude, which I call B, um, multiplied by the Pauli matrix dot, what did I use? I think I use N, okay? Where N turns out to be a representation of a unit vector using the spherical coordinates. Okay, and then I showed that it's possible to convert this time-dependent Schrodinger equation into a time-independent problem by introducing a time dependence, which explicitly says alpha beta with an explicit time dependence shall be factorized into this form. The overall time-dependent phase vector multiplying a vector which is time independent. By the way, this sort of vector is often called a spinor because this is a kind of mathematical formalism that people were using to describe the dynamics of an electron spin, which has this two-column vector description in quantum mechanics. Okay, so, and then we showed that there are two different eigenstates available, which can be written using these same angular representation as a cosine half theta, e of I phi, sine half theta, which corresponded to a eigenstate, eigenvalue plus 1. And then there was this other solution, which was sine half theta. And there's a minus sign here. Which corresponded to eigenvalue minus 1. Okay, so actually there's a way to relate these two solutions, and you can check this directly. You can go from the plus solution to the minus solution by making this change in the variables. So first you change theta to pi minus theta. Then by the rule of trigonometry, the cosine will turn into a sine, and then the sine will turn into a cosine. Okay? And now the other thing you have to take care of is this appearance of a minus sign. And that's of course quite easy. You just simply have to change phi to phi plus pi. Then that will put out an extra phase vector, which is minus 1. Okay, so I will come to the significance of these change of variables. And actually, while doing so, I will be naturally connecting these solution we have found to something called the coherent state. So the idea of a coherent state is not something completely new or completely fancy. In fact, coherent states is just a way of making a very natural interpretation of these two-level eigenstates. Okay, so in that regard, coherent state is about as natural as these. Sorry, I should say maybe I about as general as the idea of writing down the two-level solutions to the two-level problem in this form. Okay, so let me summarize the logic one more time. Any 2 by 2 Hamiltonian can be written in this way. And therefore, any 2 by 2 Hermitian Hamiltonian allows the eigenstates to be written in this way. And then what I'm saying is that these solutions, the solutions that are written in this way, naturally allows us to think about the coherent states representation. Okay, which means that any 2 by 2 Hermitian matrix, any Schrodinger problem written with a 2 by 2 Hermitian matrix allows a natural interpretation in terms of the coherent state picture. Okay, so let me see, because I don't want to write this thing over and over again. So let me cut, let me copy, and paste. Good. Yeah. So now I'm going to explore the properties of this solution. And in fact, I'm going to write them in a slightly different way. Sorry, I'm going to use a slightly different notation for them. I'm gonna call this plus n or just n, and this one I'm gonna call minus n. Remember, n was this unit vector in the classical sense, right? I have these Cartesian coordinates, and here's my unit vector, and there's this angle theta, and there's this angle phi. Now, for some reason, I'm going to write down one of these eigenstates as n and the other one as minus n. So why am I doing this? Well, because after all, this solution is nothing but the solution of this Hermitian matrix problem. Okay, so this was our Hamiltonian in the previous slide, right? I just divided out the overall factor b, and then moved it to this side where this becomes the eigenvalue epsilon. But since we're talking about the eigenvalue epsilon equal to +1 solution, then this just becomes a +1. Okay, so yeah. So this is the meaning of this state. So then I'm going to take a inner product of this state vector with itself. That is, I'm going to multiply the bra vector to the left so that the relation now looks like that. But this is equal to 1 by normalization. Okay. Now, likewise, if I take the if I do the same calculation with the other eigenstate, then what do I get? I'm gonna get minus n normalization, which is -1. Okay, Okay, so now what does that mean? Well, let me take out this vector, which is nothing but a collection of numbers, to the outside of the overlap calculation so that I can now write this in this way. Okay, so this is some expectation value, right? This is the expectation value of a spin. Okay. Well, of course, we're talking about a general two-level quantum problem, so this sigma Pauli matrix doesn't really have to represent a real physical spin. Okay, so this is a spin in a more generalized sense. Any sort of quantum system that's described in terms of two-level quantum mechanics is a kind of a spin. Okay, so and then this sigma then can be thought of as some sort of a vector representing the spin orientation. Okay, and then the fact that this expectation value of the spin orientation uh, has the overlap with the unit vector n, which is 1, means that, well, this part is kind of an interpretation, but this means that this expectation value is really just parallel to this classical vector n. Okay. Okay. And then this second calculation also shows that the spin orientation of the minus n eigenstate is parallel to a minus n, right? Due to this minus sign over here. Okay, so then we come to the sort of a physically appealing interpretation the of this end state as a kind of a vector pointing along the this direction of the n vector, and then the interpretation of this minus n state as a kind of a vector pointing along the opposite direction along minus n. Okay, plus n here, minus n over there. Okay, so this is a sort of a geometric way of representing the states, which are quantum states, of course. Okay. Okay, so this way of thinking about the eigenstates of a two-level problem is quite useful because then you can think about the dynamics of these quantum states as sort of in a motion of these compass needles or motion of these arrows in some space, right? As time evolves, this arrow rotates, kind of goes around in this space of parameters. Okay, and there's one more thing. There's one more thing we need to know about, which is that the okay, so Okay, so this expectation value is this is actually n. How do I know this? I just have to work out this expectation value for every component. Okay, so for example, in the case of sigma 1, I just have to work out this thing, okay, which is n. And what is sigma 1? It's this matrix, okay. And well, let me just try to do this explicitly so that you can easily follow. Okay, so this was the wave function. And on this side, I have to introduce its complex conjugate. So I still have the cosine half theta, but taking the complex conjugate of this will bring me this opposite phase factor, like that. Okay, then it's a simple matter of following through with the matrix multiplication to find that this answer is sine theta cosine phi, which is nothing but the first component of this unit vector. So this will be n1. All right, so you can make a similar calculation for sigma 2 and then sigma 3 and just recover all these other components. Okay, but n is a unit vector. And what that means is that this expectation value can only move around on the surface of a unit sphere. Okay, so this is my unit sphere, and this arrow represents n, which also represents the expectation value of my effective spin operator. And this kind of sphere is famously called the Bloch sphere. This is named after a famous physicist, Felix Bloch, who was actually the first ever PhD student of Werner Heisenberg. Initially, he thought about the motion of electrons in a crystal and came up with his famous theorem called the Bloch's theorem. But after that, he switched his interest to spin dynamics and did lots and lots of interesting things, including the development of a nuclear magnetic resonance machine, for which he won the Nobel Prize. So he was starting out as a first-class theorist, but after switching to an experimental physicist, he got his share of the Nobel Prize for his experimental work, not theoretical work. So that was quite a remarkable career for him. Okay, and okay, so the lesson is that the movement of, well, I should say the time evolution of a two-level quantum state can be pictured as the rotation of this unit vector arrow over time on the surface of this unit sphere called the Bloch sphere. Okay, so this is the evolution of a two-level quantum state. And this is nice because although quantum state is a pretty abstract thing, but through this mathematical trick or mathematical insight, we can use this geometrical means of visualizing what it does over time, right? So this is more like a classical way of thinking about the particle motion, namely the particles are moving through space as a function of time. And this is some sort of a motion, although not of the particle coordinates, but maybe you can say this is something like a quantum coordinate. And this quantum coordinate moves around in this quantum space, not the real space, like this. Okay? So Bloch sphere, let me just emphasize it one more time. Bloch sphere was an idea introduced in the context of the spin dynamics, but exactly the same idea applies to any sort of two-level system. And I guess that's something I just cannot emphasize enough. Okay, one final comment. So now have we completely solved a two-level problem? I so far I gave you the impression perhaps that it has been, but the actual answer is a resounding no. Well, because of the following reason. So I made this substitution of factoring out these overall factor in the Hamiltonian, and then writing the other components in this polar coordinate representation. And then taking care of the task of diagonalizing this 2 by 2 Hermitian matrix to find out its two eigenvectors. Uh, and the reason why we could accomplish that is because we assumed that the time dependence was all in here as a simple phase factor. And then the remaining factor was assumed to be time independent. However, that's really only works if we assume that none of these other things were time dependent. But in general, there's no reason why it should be, right? So even this b can be some function of time. So what I'm saying is that this entire Hamiltonian can be a function of time. Okay, so in fact, the general two-level problem would be that of solving this sort of coupled differential equation where the elements of my 2 by 2 Hamiltonian matrix are all time dependent. And when the Hamiltonian itself is explicitly time dependent, then all the tricks that I have been talking about literally fails to work. Okay, and the simple reason is the following. When you do this, you can factor this out, but these other things also, the remaining alpha beta factor, they also have to become time dependent. So therefore, then this time derivative thing becomes this times alpha beta plus I delta t acting on alpha beta multiplied by the phase factor. Okay, So the bottom line is that there's this factor that we did not have to worry about before, but now cannot be ignored because these two things still continue to be time dependent because the elements in the Hamiltonian continue to be explicitly time dependent. Okay, so the bottom line is that you cannot solve the most general two-level problem except when the explicit time dependence in the Hamiltonian is missing. So if you don't have an explicit time dependence in the 2 by 2 Hamiltonian matrix, then everything I have been saying to you works and you have a perfectly complete solution at your disposal and with all that block sphere interpretation and so on. So then are we at a loss when it comes to okay, are we lost for time dependent Hamiltonian? Well, yes, for the most part. But there's a famous exception. Okay, called the Rabi problem, which allows an exact solution despite being an explicitly time-dependent two-level problem. And okay, so I will eventually find time to talk about this Rabi problem, but let me just emphasize here that the this exact solution of a time-dependent two-level problem prompted a the idea of a explicit time dependence to control the state of the two-level system. And that idea of controlling the quantum states through explicit time dependence is at the foundation of many of the things that we now know about, including the quantum computer, and even the idea of a laser comes from using this explicit time-dependent control of the quantum states. Okay, so of course that all sounds very fancy and vague, but I hope I can make it more transparent in the course of this lecture. So please wait around.